It's interesting, but it's a little bit hard to understand.
That's right. It's interesting but hard. But remember, the thing which you do, and also the thing which Philip did in our workshop, which we did, is a very, very advanced topic. And people normally, when they just go for PhD in different fields or the master program, maybe almost 10 or 12 years older than you, they just start working on those stuff. And it's good that at this early age, you are getting exposed to this stuff because, it gives you some, vision how the math is going to be relevant to a grand scale in, let's say, solving a problem, and that's a good thing. But if you think this is hard, it's true, this is hard, but beyond it, it's oh my God, I have no words to describe the future which brings it for you then. Okay. For example, Philip and also Rose, listen to this. For example, the thing which you do, for example, right now for modeling, right, Rose? The codes which you write, and also we worked at tonight then. For example, you can work it on a little more interesting stuff. This is called neural network. When you work on your project for the Hodgkin-Huxley and you see how the neuron works, you can combine that knowledge also with the math to write a code, which is not very hard, but it's very, very interesting. For example, to predict that based on the CT scan, if someone has a breast cancer or not. It's unbelievably interesting. And if you are interested, I can provide you some sources to learn those stuff. Then your future is going to be tremendously good and lots of intellectual. Okay. And I see that the Gloria hasn't yet joined. Probably he joins after the break. Let's start the lesson right now. Okay. Now, guys, the thing that we did so far in our course, especially the course that we did yesterday, was this one that we talked about the inverse of a function. Previously, function, I should say at the beginning of the term, we talked about the inverse of a function, but at this stage, we talked about the inverse of just a trigonometric function. The inverse of a trigonometric function somehow appears to be much easier in terms to deriving it, because those 4 steps that we learned, it can be truncated from the first step, then you jump to the 4th state and 4th step, and you do not need to just do the things which is in between. And that's the thing which I'm going to do this right now. We just start from a very simple example. We follow those 4 steps and we show at the end what could have been done even much easier. You remember that we talked about the function f of x. We talked about it as a tangent of a single variable, and that variable which was randomly changing, we call that the x. When we talked about the x as a random variable and the single variable of the model, we come to understand that from the x as a variable space, we make projections to the range of the f of x. And now it's a forward looking of this transformation which the function does. The thing which we want to do right now is that we want to take a step back and look at it as in the reverse order to see that how we can just move from the range to the domain. That's the plan. So far you have seen it, and you see that it happens in 4 different succinct steps. The first step is that, as what you have learned, it just starts from the function. I call that step number 1. For step number 1, you saw that you replace f of x with y, and simply it becomes, it turns f of x equals to y equals the tangent of the x. Do you see what I'm writing? The color is good, the light is good, everything is fine, guys?
Yes.
Okay. Then from step 1, you go to step number 2. Step number 2, what was that? For step number 2, we said that this is turning to be this one. We say that the tangent of the x, we say that for step number 2, wherever we see y, we start walking from the left. Wherever we see y, we turn it to the x. And wherever we see the x, when we move towards the right, we put that y. We only rename the variables from x to y and y to x. To go to the step number 3, the thing that we learned was that we say that, okay, at this step number 3, based on the things that we learned, when we see the y, whatever we can do, we have to do that in order to have y being isolated in one side of the equation. By isolation, I mean that we have y, which has the coefficient of 1 and the power of the 1, and the y is expressed fully in terms of the x. With this one, when we have the tangent of the y, in order to get rid of the tangent, you will see that later when we talk about one identity, you think that you can get the inverse of it right away, although we do not know that right now, and we end up by this. Tangent inverse of the x becomes y. Its tangent minus 1. I have to remind you that minus 1, it's not the power, it's just a symbol which signifies and yells at you to say that, okay, I'm the inverse of the tangent. And that's what's the purpose of the tangent of the x. And at the end, as step number 4 that we learned, we again go back to change y to f minus 1x, which shows that the inverse of the f of x, because f of x, it was a machinery which it was making a forward transformation of your variable into the range. Now, when we talk of inverse f minus 1x, we say that, okay, now we are taking the reverse direction. Now we are moving backwards, which is essentially tangent minus 1x. And sometimes also, we said that f minus 1x, instead of writing tangent inverse, we call that arc tangent of the x. These two essentially exactly are the same. It's your artistic choice that if you like inverse of the tangent or the arc tangent of the x, but both of them represents the reverse transformation from the range backwards to the domain. Now, any questions, guys, so far?
No.
No questions? How about you, Philip?
No.
No question? And now, I go back there, then I say that, okay, the beauty of some of these trigonometric functions is that sometimes in order to start from the forward transformation to the reverse transformation, there is no need to take step number 1, step number 2, step number 3, and step number 4. The only thing which you need to do is this. You come here, right from step number 1, jump to step number 4. Okay, you say that if I have a function which is tangent of the x, its inverse is arctangent of the x, or tangent inverse, and I do not need to take these kind of steps. And that's a good thing about the inverse of the basic trigonometric function. You just right away starts from the step number 1, you find yourself at step number 4. No need to take step number 1, 2, and 3. Everything is fine, guys?
Yes.
Yeah. Philip, everything is good with you also?
Yes.
Okay, I'm gonna then go back to this one. Okay, and now the thing that we do is this. We say that, okay, now, in order to make a comparisons, we say that, okay, we just start from here. I'm just going to plot as what we did before to put the things in a kind of a chart things, because it makes it very easy to make some comparisons. We call this domain. We call this range, and this one is going to be the function. Okay. The first thing that we start, we call that, okay, the first function, it's going to be, because we're talking about the tangent of the x, I'm going to write the tangent of the x. Okay, now, guys, the thing is that for the tangent of the x, I'm looking at this first cell here, which denotes the domain of my function tangent of the x. And my question for you is that, what is the domain of the tangent of the x? Anybody knows? Philip and Rose? Okay, when I was at your age, I had always a problem with the tangent of the x domain. Let's see how to get the domain of the tangent of the x. I'm going to put that paper momentarily aside. I'm going to go back to this to fill out these 4 cells which we have. Actually 5. We have 1, 2, 3, 4, 5. But temporarily, in order to explain the domain of the tangent of the x, I'm just going to change my paper. I say, okay, f of x is the function which we call that the tangent of the x. And now, guys, when we want to talk about the domain of that function, we very simply, we can find the domain in that manner. We do not right away go to the tangent of the x. But based on the definition that we know of the tangent of the x, can I write tangent of an angle or variable x as a rational expression of a simple ratio, the sine of the x over the cosine of the x? Can I do that? Because that's the basic definition of the tangent of the x. When we talk about the trigonometric expression, we saw that the sine and cosine are the most fundamental, fundamental expressions, because the rest can come from the manipulation of these two. The tangent is the sine over cosine, the cotangent is cosine over sine, the secant is 1 over cosine, the cosecant is 1 over sine. You see, you can get everything from sine and cosine. The definition of the tangent is sine over cosine. And now, it is very reasonable to say that when I'm looking for the domain of the tangent of the x, it's very relevant. It can find the domain of the sine x over cosine x. Does it make sense to everyone?
Yes.
Yeah? Okay. Yes, Philip? Philip, does it make sense?
Yes.
Okay. Okay. And now, in order to find the domain of sine over cosine of the x, which I noticed that the domain is going to be the same exact thing as a tangent of the x, then I look at the expression. I see I have a rational expression which at its denominator, it has a function. You see cosine of the x, guys? It is at the denominator. And we have so far seen that the functions which they have a denominator can become very sick, very ill, and we have to take them to the doctor. And they become sick when we feed them with some foods that they become zero at the denominator. Then we have something over zero divided by zero, which it becomes like the function vomits. Then we have to find where cosine of the x becomes zero. That's right, and that's the question. Where cosine of the x becomes zero, that it makes the whole expression to vomit, to become sick, to die. If I know these points, I can exclude them. Exclude them from the R, from the all real numbers, and I say, okay, the domain of this function then is all the real numbers except those ones which makes cosine of the x to go to zero, because if that happens, the whole function vanishes. And now, what do? We come here to answer that question. In order to answer that question, I'm just going to come from here. Everybody sees what I'm writing?
Yes.
I'm going to come here and talk about this question, that cosine of the x becomes zero. This becomes the equation which I'm going to solve. And essentially, guys, it is going to be the very first trigonometric equation that you're going to solve, which is congratulations to you, because that's very interesting. Then now, we have to come to find the solutions for the cosine of the x equal to zero. If I find the x, then I exclude it from the R, then I say it becomes the domain of the tangent of the x. And you got, what's the plan? What's the mind plan? Yes, everyone?
Yes.
Great. And now, in order to answer that question, what I'm going to do, I'm going to, as usual, go to plot my unit circle. It becomes my x-axis. It becomes my y-axis, and that's the origin. And I'm going to draw a circle. I hope that you see the circle. It's drawn by pencil, and sometimes pencil is not a very good medium. Okay, now, look at that. With this very special case, I say this one, it's gonna denote my angle as alpha for a point on the circumference of this unit circle, which I'm gonna call it, I can call it anything, but I call that P, which stands for the point, and P, that's why I call it P. The angle is drawn, the central angle as alpha, and the P can rotate clockwise or counterclockwise or clockwise, but this time it's counterclockwise. And we know that if that's the unit circle, guys, the projection to the x-axis, which it shows the x, it denotes the cosine of the alpha, right? Because based on the things that we learned, the cosine of alpha, you see if I write it here?
Yes.
Awesome. We know that the cosine of the alpha becomes the expression of the x divided by the r. R is the radius of the circle. And if it's equal to 1, because that's the unit circle, which it means that the length of the radius is going to be unit in length, 1 centimeter, 1 meter, 1 kilometer. Then it becomes x divided by 1, then it becomes x. Then it shows that on the unit circle, when the point P rotates along the circumference of the unit circle, at any point which it stops, the x coordinate of the P, because you know P has a coordinate of the x and y. Always the x coordinate of the P represents the cosine of the alpha, which is segmented by this point P. And now, which points, I'm going to answer this question because based on the summary which I mentioned, what we are looking for, we are looking for to answer that question, what is the cosine of x? When the cosine of x becomes 0. When the cosine of the x becomes 0, it means that where can I find the x on my unit circle that its projection on the x-axis becomes 0, x becomes 0. Where are they? I can just start from, let's say, go to this point. You can see this point, guys, on the y-axis.
Yes.
What is the angle for it?
Pi over 2.
That's right. Correct, Philippe? Is it correct? Pi over 2. And how about this point? This point, the cosine is x is minus 1. I'm totally fine. I come to this point. This point also, the projection to the x-axis, it goes all the way to the 0, the origin of the Cartesian frame, which it means that the x is 0. Then what angle is that?
3 pi over 2.
That's right, 3 pi over 2. Then I go back again to the circle. Go back to the point pi over 2. Which point is that going to be? I moved from 3 pi over 2, I added pi. Because you know, when you are rotating the p's along that circle, it can rotate around that circle forever. In the next 100 years, it rotates, and picks different points. And it doesn't stop at all. Then from 3 pi over 2, it can again move back to this point, which it means that it takes half of the circle. Half of the circle is pi. Then 3 pi divided by 2 plus pi becomes how much? Guys, please add this. 3 pi over 2 plus half a circle in radians, which is pi. 3 pi divided by 2 plus pi becomes how much? Yes, Philip and Rose?
Yes.
How much do you get? 3 pi divided by 2 plus pi.
5 pi divided by 2.
That's right. Then 5 pi divided by 2, you are here. You keep moving. You do not stop. You take another half of the circle, which is pi radians. Becomes 5 pi divided 2 divided by the plus pi. Becomes how much? Five pi divided by 2 plus pi. How much do you get?
7 pi divided by 2.
That's right. You are here. You move back again. Another half a circle to go back up there. Becomes 7 pi divided by 2 plus pi. It resembles like the Markov chain. Each step depends on the previous step. 7 pi divided by 2 plus another pi. How much do you get?
9 pi divided by 2.
That's right. Then guys, you see that each these points, and you can keep continuing, 9 pi divided by 2, 11 pi divided by 2, 13 pi divided by 2. It goes forever. Then you see this trend that if x equals to, let's say, n plus 1 over 2 times pi, where n can be 0, can be plus or minus 1, can be plus or minus 2, goes forever. Then if x is this, cosine of the x becomes 0, correct? For example, when n is equal to 0, becomes pi over 2 that we saw. N equals to plus 1, becomes 1 plus 1 over 2, becomes 3 over 2 times pi. N is equal to 2, then it becomes what? 2 plus 1 over 2 becomes 5 divided by 2 times pi. And we have minus in case if you just want to just move counterclockwise. Then you see that when x equals to n plus 1 over 2 divided times pi, the cosine becomes 0, then it causes a problem for the tangent of the x. Guys, do you feel it? Do you understand it?
Yes.
Yes, Rose? How about you, Philip?
Yes.
Then we see that here, that if x becomes any of these kind of values, cosine becomes 0. When cosine becomes 0, you have a problem for the domain of the tangent. Then for the domain of the tangent of the x, then for the domain of the tangent of the x, the domain becomes what? X becomes all the real numbers except that the x should not be equal to n plus 1 over 2 times pi. Make sense, guys?
Yes.
You see what have I written here? You can see that clearly?
Yes.
Thanks. How about you, Philip?
Yes.
Awesome. Then you will see that the domain of the tangent was not directly inferred. In order to find the domain of the tangents, I had to just express that as a sine over cosine of x, then find the points that the cosine becomes 0. Then I just came to solve the very, very first trigonometric equation. And by using of, I should say, the unit circle, I found that x becomes these, that makes the cosine goes to 0. Then I remove it from the r in order to define the domain of the tangent of the x. Correct? Now, then as a result, I'm just gonna, any questions, guys, so far? Nothing?
No.
No? I'm gonna, guys, share my screen with you, that I have the plot of the tangent to show that to you. You all see my screen, huh? Look at that. I have the tangent of the x plotted. You see the blue lines, the blue plots, the red plots? These are the tangent. You see that for the tangent of the x, there are some points that the function is not along the x-axis. You see that? For example, here, the function goes to infinity. You see? These are from 0 to plus x, from 0 to the right side. These points for example, you can see this here. You see this point? These points, which is going to be before 2, this, for example, it becomes n plus 1 times p. This one, again, the same thing. To the right side, these points, which they are not part of the domain, is n as minus plus 1 over 2 times p. Then you will see that it's how the domain is formed. And these points which you have to exclude it shows that the graph is not continuous along the x. It's chopped along the x. You see that, guys?
Yes.
But how about the range of the function? What is the range? What is the range? I mean the values along the y-axis. It from 0 goes to infinity, from 0 goes to minus infinity. It means the range is what? Are all real numbers. Does it make sense, everyone?
Yes.
Yeah, any questions?
No.
No? How about you, Philip?
No.
Awesome. And now that we solve this one, I go back to this, to the main chart which we had. We saw that the domain of the tangent of the x can be any real number except these points, but for the domain of the tangent of the x, when I'm talking about the inverse of it, because I know that I'm just going talking about the tangent inverse of the x, I have to shorten my domain, otherwise life becomes so hard. Any number becomes, any arguments of the tangent of the x, it would go forever, and that's not what we want to have. Then I'm just gonna truncate the domain of the tangent of the x, not for all the real numbers. I'm just gonna truncate it, and I'm gonna follow the domain that I did for the sine of the x. For the sine of the x, if you remember, we talked about the domain. And we said that the domain is going to be from what? It's going to be from minus pi over 2 to plus pi over 2 for the sine of the x. Do you remember that when we truncated the domain? But the problem is that if I follow the same trend of the sine, minus pi over 2 and pi over 2, they are essentially the roots of the cosine of the x that makes the tangent of the x to behave crazy. In order to exclude them, the interval which I show, it's going to be in the parentheses. Previously, when we talked about these ones, about the intervals, which we talked about that before, is this, guys. When we define an interval, we have either the brackets or the parentheses. If I say, for example, plus, for example, pi over 2 to 3 pi over 2, which I have brackets to both of them. You see that? What do I mean? I mean that on this interval, which expands from plus pi over 2 to 3 pi over 2, because both sides have the brackets, pi over 2 and 3 pi over 2, they are included in that interval. However, if I show that by, let's say, pi over 2 and 3 pi over 2 with parentheses, it means that the boundaries, which is pi over 2 and 3 pi over 2, they are excluded. And whatever is in between, it can be included. Right? Do you see the difference?
Yes.
Does it make sense to all at all?
Yes.
Yes, Philip? Philip?
Yes.
Does it make sense?
Mm-hmm.
That nice. Then whenever you have parentheses, it means that these two numbers, the neighbor numbers. They are not included in that interval, but whatever is in between is included. For example, pi over 6 is included. 0 is included. For example, I give you a number, an interval with not the pi. For example, imagine between 1 and 5. The interval is with the bracket. It means that 1, 2, 3, 4, 5 is included. But 1 and 5 interval with parentheses, it means that 2 is included, 4 is included, 0 is included, but 1 and 5, both of them, they are not included. Huh? For example, I say 1, 5, bracket for the 5. What do I mean by this interval? It means that 1 is not included, but 5 is included. You see the bracket shows the number which is attached to that is involved, but parentheses means that the number which is attached to parentheses is excluded. They are not in that interval. Okay, guys, you got it?
Yes.
Awesome. Then when I have the domain as minus pi over 2 to plus pi over 2, then when I do have it, it means that anything inside is included except minus pi over 2 and pi over 2. And also about the range, I know the range is going to be all the real numbers for the tangent of the x. And now, I'm going to this one for the tangent inverse. I say this one, then we take a quick break, then we come back to do some very interesting examples of these type of functions. Okay, with the inverse function that we talked, we saw an interesting property that the range of the forward transformation, it becomes the domain of the inverse function. And it means that the domain of the tangent inverse of the x becomes the R. And we saw that also as a general rule that the domain of the forward function becomes the range of what? Of the inverse function, which it means that minus pi over 2 and pi over 2 becomes the inverse of that function. Okay. Any questions, guys?
No.
No? Philip?
No.
Okay. And now, we essentially need to know these kind of stuff when we move forward, when we come back from the break. We're going to talk about how the argument of the inverse of tangent can take any arguments. For example, on Friday, you saw that. We saw that on the things that we discussed. For example, you saw that when we talk about the sine inverse of, for example, let's call that, for example, 3.4, we say that this function is not valid. Why? Because we saw that the sine inverse of x has to be between -1 to +1, but the argument was outside of that scope. That's the thing we covered on Friday. But as a comparison, you see that the tangent inverse of, let's say, for example, 21.4 also is valid, because as what we learned right now is that for the tangent inverse of the x can belong to any real number, provided that you get the tangent -1 of this argument to find itself between these two values, pi over 2 and minus pi over 2. You put that in your calculator. If the answer is out of the scope, it is not valid. And we saw that for this one, it can be any number. It can belong to the R number, the function itself. These things which I know, I got the information of how do I know that the argument of the tangent inverse can be any real number, and the function itself, the output, should be between minus pi over 2 and pi over 2. How do I know that? I know this from this chart, which I derived it here based on the properties of inverse of a function, that the range and domain of the functions becomes exchanged. Any questions, guys?
No.
No? How about you, Philip?
No.
No? If you have no question, the time is now. We take a break. I think that's the right time to take the break. I think now this is 12:05. We come back by 12:20. Is it good?
Yes.
Yeah, awesome. Then I see you guys in 15 minutes. Enjoy your break. And also, I'm going to take a break myself. See you soon then. Guys, welcome back. Okay, are you there?
Yes.
Awesome. Okay, now I'm just going to say one more property of these inverse functions between, I should say, the forward transformation as a tangent of your variable and the arctangent of your variable as an inverse, and which is a composite function. Then we just solve two examples, and essentially that should be all the dose for today then. Okay, what we learned before, we know that you can make a composite functions. We have done that many times also with the sine and inverse of the sine, that we saw that the composition that you make of a function with its own inverse, which it means that, for example, you have the sine of, for example, the arc sine of the x. That's what we did, I should say, on Friday. We said that essentially that's the composition which you make of the function with its own inverse. You see that sine and sine? It always takes you to this argument, x. We saw that also we can extend this model into this property for, I should say, for this tangent of the x, that we say that we make a composite function of the tangent of the x with its inverse, and we come to these two identities, that the tangent inverse of the x equals to the x. And you know that also you can make the inverse, I should say, the compositions from the other side. You can say that, okay, the tangent inverse of the tangent of the x also, it equals to x. These are the two identities that we can directly get them from I should say, the things that we talked about that many times since, I should say, the second week of the class, how to make a composite functions of a function with its own inverse. And now, if you have no question, which I'm just going to go to just solve one example. This example is going to be a very interesting one. One of two examples, we're just going to solve it for today. For this example, I'm just going to say that, okay, find the tangent of the arc sine, the inverse of the sine of -1/2. Okay, we are going to evaluate this expression. Okay. And now, in order to solve it, I'm going to solve these two for you directly. Then I just post the homeworks for you. You have many of, I should say, examples like this, which it's a good practice for you. But I'm just going to review of the method we covered last week, then do the second example. Then you should be very good, on a good seat when you just do the assignment then. When we work about these ones, we talked about that, we call them a kind of a mixture model. Because it's a mixture model, because we are talking about the tangent of the arc sine of one number. They are not from the same nature. We are not talking about the composition of the tangent with its own inverse. We see that the tangent is composed with the inverse of a different function. Then it's not going to be as easy as, let's say, the tangent of the arctangent of x, which becomes x. It involves more calculation. But how to do the calculation, I called, if you remember, I talked about the method that we talked. The method was the thing that we said that it's going to be the kind of an onion rule. We said that, for example, when you did the cooking, you cut the onion with the knife, you go all inside the onion into real core, and you talk about the one which is inside, we call it what? We called it the core function or the inner function, just the core of the onion. And also, we talked that, okay, for the tangent, which is the outside, we call that what? We call that the outer layer. It means the function which is outside of the peel. You peel the onion's outer layer to just go inside the core. And the method that we derived, I should say, a couple of days ago, we said what? We said that for the arc sine, of -1/2, we start from, let's say, the inner side, the core of the function. Then I'm just going to go over here, talk about what is the arc sine of -1/2. I'm going to start with this as the core of the function. I ask myself then, what is the arc sine of -1/2? That's the thing which we were going to talk about. And now, in order to answer these questions like that, we learned that it's always much easier to go to the other side of the coin and ask ourselves, what is the forward transformation? What is the sine of the angle which becomes -1/2? It's always easy for myself that whenever I'm just going to answer a reverse transformation, I go to the forward transformation and find it there, then find the answer for the backward. Then I ask myself, if I have an angle which I do not know, in the forward transformation, I can ask myself, what is the angle that its sine ratio, it gives me the answer of -1/2. If I find this angle, it's going to be the same answer for its inverse function, because these are the two sides of the one coin, which from both sides, the coin has the same value. There is no difference. But what is the angle that its sine becomes -1/2? How much?
-π/6.
-π/6. How about you, Philip? How much did he get? Philip? Philip? Mr. Philip? Maybe he stepped away. That's right. It becomes -π over what? Yes, Rose, -π over 6. It gives me the answer. And now, then it becomes very easy. Then I can just, then I resolve my issue. With the core of the onion, I put the other layer to wrap it around the outer layer. For example, it becomes what now? Becomes the tangent of what, Rose? Minus pi over 6. Because the core layer, it gave me this answer, huh? And I wrap the outer layer around the core when I resolve my issue with it. Does it make sense, Rose and Philip?
Yes.
Now, I come to answer that question. Now, what is the tangent of minus pi over 6? If you are confused sometimes how to find this one, we can always work like that. We said that we use again the definition of a tangent, that it's a function which is denoted by the sine of minus pi over 6 divided by the cosine of minus pi over 6. That's right. But what is the sine of minus pi over 6?
Minus
Minus what?
minus 1/2.
That's right. We have it also there. Philip, are you there?
Yes.
Does it make sense to you, the things which we do?
Mm-hmm.
Are you sure? You see that the sine of minus pi over 6, it's essentially minus sine of pi over 6. Do you remember that trigonometric circle?
Yes.
Yeah? And also, for the cosine of pi over 6, it's essentially, how much is that? It's the cosine of pi over 6. I'm gonna explain about the things which I'm doing right now in a second. I'm gonna explain about these things which I'm doing in a second, but please bear with me. If you have a problem, Philip, I'm just gonna talk about that in a second, that how these things works. But the cosine of minus pi over 6 is essentially equal to the cosine of pi over 6, correct? What is the cosine of pi over 6? How much is that?
Square root 3/2.
That's so true. Then what is the end result? Minus 1 divided by square root of 3. You can also rationalize this expression to go to this result, that minus, after rationalization, I'm not going to do that, but it's going to be the end result. And then we just did this one like that. Does it make sense, everyone?
Yes.
Yeah. How about you, Philip?
Yes.
Yeah. And I told you, because some tricks is going to be for this part, that when we have the minus of the angle, I'm just going to very quickly explain why the cosine of minus pi over 6 is equal to the cosine of pi over 6, but the sine of minus pi over 6 equals to minus sine of pi over 6. I'm going to explain that very quickly here before we move on to the second example. Guys, what time is it now?
12:33.
Okay, we have enough time. I'm going to very quickly explain that again, that we have covered that also before. I'm going to show again the Cartesian coordinates Philip, listen very carefully with the unit circle. Wrapping around it. It's going to be my x-axis. It's going to be my y-axis. And the thing which I do is that I come here, I grab 2 points. On my unit circle. The first point which I have, I'll call this P. And the second point which I have, I call that P prime. But what is their difference? P is a positive angle because this is counterclockwise. I call that alpha. But P prime is counterclockwise. I call that minus alpha. Because we learned that convention that rotation counterclockwise on the unit circle, it produces positive angles. The rotations counterclockwise, conventionally, it produces negative angles. If I have a unit circle, which it means that the radius r and r is going to be 1, then the sine and cosine of these points is very clear how to find it. The sine, the cosine represents the x, projection to the x-axis, and the sine is projection to what? To the y-axis. Am I right, Philip? Philip?
Yes.
Am I right? Nice. For point P, if I assume that the coordinates are x and y, y is going to be this, x is going to be this, and for this one is going to be minus y. If this is x and y, for pi prime, what is the coordinates, Philip? If you compare with that one, you see they have the same x, but their y's are reflected throughout the origin, and this is minus y. You see that, Philip? If that's the center? Yes?
Yes.
Okay, and now take a look. Based on the definition of the unit circle, we previously said that you can define the sine of an angle as its y coordinates divided by the r. And in the unit circle, as the r is equal to 1, then the sine becomes always y, correct? And for the cosine of the alpha, we learned that we can define it as the x coordinate of your points, pi prime or pi, divided by r. If r is going to be 1 in a unit circle, then the x always represents the x-axis. Then you see that, Philip, as long as the p or pi prime rotates around, their coordinates represents their cosine and their sine, if the radius is 1. Now look at that. For the angle alpha and minus alpha, it can be pi over 6. You see the x is the same. X represents cosine. Then it means that for the angle alpha and minus alpha, because they have the same x, the cosine is going to be the same. But for alpha and minus alpha, like pi over 6 and minus pi over 6, you see their y coordinates is plus y and minus y, which it means that y is represented by the sine. It means that their sine is going to be minus of each other. Does it make sense, Philip? Yes?
Yes.
Fantastic. I love these geometric representation of the trigonometric ratio. They are so much fun to look at them. Okay, any questions, guys, so far?
No.
No.
No? Okay, now we just go to the last example. What time is it, guys?
12:40.
12:04. Oh my God, that's fantastic. We have sharp half an hour and we can focus on the second example, which is going to be crucial for us. I'm going to talk about this expression. What is the tangent of let's say tangent of sine inverse okay, minus 8 divided by 17. Okay. And now, guys, now we are focusing on this example. Somehow similar to the previous one. Previously, we had what? The tangent of arc sine of -1/2. Now, we are going to find this one. But what is the difference between this one? Look at that. For this example, they are exactly the same thing. You see that? We have a tangent as the outer function, and we have arc sine, which is the same thing as sine inverse. They are the same thing. We had previously -1/2, which it was a reference angle because we know that the arc sine of -1/2, it's easily derived as it becomes -pi/6 because there is no quotient out of it. But for this one, we have arc sine of -8 divided by 17, which doesn't represent a reference angle, which is easy to work with. You see the difference now? Yes? And now, if you see this difference, then it's not going to be as easy to find it as what we did before. I just give you 2 seconds, 2 minutes to you think of it, do some preliminary work, then I solve that for you. Guys, did you solve it? If no, listen exactly to what do I do. On Friday, we somehow solved this kind of stuff. We said that when we do not have the reference angles, when we have Nichtsch's model like that, still we follow the same rule that we learned. Still, we go by the onions rule. We say that, okay, this inner term, it is going to represent what? It is going to represent the inner function or the core of the onion. And this tangent is going to play the role of what? Of the outer layer, okay, of my onions. And you're now trying to see what's going to happen. Previously, we had some sort of similar things, but we used a geometric representation as a right triangle to solve a right triangle for these ones. But for this one, it's the same similar thing, but the geometric representation is going to be somehow a little bit different. Instead of right triangle, we're going to use the unit circle or the circle to represent the geometry expressing that trigonometric function. I start from the inner function. I'm going to start from this. I remember the example which we had. I said that, for example, Rose has the knife cuts the onion, remove the core of the onion, which is going to be the sine inverse of minus 8 over 17 on a plate on the dining table. And Philip suddenly shows up and asks, wow, what is that, Rose? And Rose is going to give a name to this core, I should say, part of the onion, in order to introduce it to Philip. Then says that, Rose says that, okay, it can be called alpha, it can be theta, it can be A, B, any number, any name, not the number, any name. I choose it alpha because I like the way which it's written. You can call it A, beta, B, any Greek letter or Latin letter. I call this. Okay. The next step which we do, I know from the things that I learned, I know that I can make it to be very simple. I know that if I come here and I take the sine from both sides, essentially I have made a composition of two functions of the same nature. What do I mean? I take the sine from both sides. I take the sine of sine inverse of minus 8 divided by 17 equals to what? Equals to sine of alpha. Correct? But look at this one here now. I have the composition and the mixture model of a forward transformation with its inverse, which both are from the same nature. I have sine, I have inverse of the sine. Then what is that going to be based on the things that we have learned? We know that the sine of sine inverse of the x becomes what?
X.
X. Do you see this color, guys, or no?
Yes.
Okay, nice. Then as a result, what I derive here from this thing, it becomes what? It becomes sine of sine inverse of that thing becomes minus 8 divided by 17 should equals to sine alpha. It is going to be the thing which I derive it from here. I'm going to highlight it here. Okay, now we deduced this expression to here. And now we say that now, okay, the sine of alpha, it's minus 8 divided by 17. Guys, any questions so far?
No.
No questions? Okay. How about you, Philip? Philip?
No question.
Are you sure?
Yes.
You were hesitant about it. Okay, now, I'm just going to take this one to the next page. I'm going to take this one to the next page and continue from this. Still, I'm trying to resolve the thing which happens with the inner function. I'm going to say what? I'm going to say here that I learned that sine of alpha was how much? Minus 8 divided by 17. And now, if you remember from the previous session, which it was a Friday, when I'm at this stage, I have to just express this equation geometrically. Last week on Friday, we had something similar. I had x instead. I didn't have any numerical valuations. Then I tried to use, I should say, the right triangle, if you remember from the example which we had on Friday. But now I have a numerical evaluations of my angle alpha, which is minus. The easiest way is that I just use what? I use unit circle in order to geometrically represent this equation. It becomes my x, it becomes my y-axis, and that's the origin of my axis there. And I'm just going to plot this circle, and I'm going to localize this function there. But how do I show that? I have to show the angle. But in order to show the angle, I know the angle has two arms. The first arm is always on the x-axis, starts from some points on the circumference of the angle, then it goes to the origin, it becomes the center of the angle, and the moving arm is, I assume that it's gonna just move counterclockwise, and it has to stop either at the first quadrant, second quadrant, third quadrant, or the fourth quadrant. But there, in order to understand where the moving arm has to stop, I take a look at this. I have sine alpha is minus 8 divided by 17. The sine is minus. Look at this, the sine of the alpha is minus because it's minus 8 divided by 17. Then where do I can find which quadrant produces the minus sign? Any quadrants which is lower than the x because they have the minus y, correct? Then it means that my candidates for this is either quadrant 3 or quadrant 4. It's gonna be quadrant 3, it's quadrant 4. Does it make sense, guys?
Yes.
Yes? But guys, remember the very important thing on this. When I go back to, but the question is that between my candidates, which is quadrant 3 or quadrant 4, which quadrant is going to be, should I write my angle like this? It comes all the way here and I have to draw a line there, or I have to draw a line here. Which one is that? Then in order to answer it, to find only one candidate, go to this, to the things that we talked last week and the chart which we produced. Look at this expression that we have, which is inverse of the sine, and see the chart which we produce, how important they are. Look at this function. Let me also find the lesson from last week. And luckily I found it. Look at that. Do you remember, guys, the chart on the first day of the inverse of trigonometric function? We said that the inverse of the sine, the arguments which it take, the x, can be between -1 and +1, but the whole function, which is y, it has always to be between -π/2 and π/2, correct? Do you remember this chart? Philip and Rose?
Yes.
Yeah? If you remember this chart, now I go back to this. Oh, there is my page. Okay. I go back to this. Look at that. Alpha, which is the inverse of sine of anything, is the inverse of the sine. Then alpha, what is the range of the alpha as a function which is the arccosine of something? The range is going to be between minus pi over 2 to pi over 2, right? Then it means that from this expression, we get this very important fact that alpha, our angle which I'm trying to represent that geometrically, has to be between these 2 points, plus pi over 2 and minus pi over 2. Correct? Based on the chart which I know from last week. Then I know that the angle which I'm representing, which its sign is minus, is also has to be between minus pi over 2 to plus pi over 2. What is plus pi over 2? Is this. And where is minus pi over 2? Philip and Rose. Minus pi over 2, it means that you pick up an angle but move clockwise. You start from here, you go here. This one can be minus pi over 2 if you connect it from here, from the clockwise. But if you move from there, it becomes 3 pi over 2. But from here, it becomes minus pi over 2. You see, it's very interesting, huh? That's the beauty of, I should say, trigonometry. Counterclockwise, you get a different value. Clockwise, you get a different value. Then it means that if alpha is between minus pi over 2 and pi over 2, it has to be between the right cycle. It's going to be on the right half of my circle. And at the same time, its sign is minus, which it means that it's going to be between quadrant 3 and 4. And if you combine these two criteria, you see that the angle has to be on the quadrant number 4. And that's why I come here and put the angle like that, and it represents my angle, alpha. It was a little confusing, I guess, huh? Guys, ask me any questions so far if you have. Oh, guys, Philippe, Gloria? Oh, sorry, Rose. Philippe and Rose, any questions?
No.
No.
Are you sure, guys? Everything is fine?
Yes.
And you had no problem to localize the angle, huh? Based on this fact and this fact. Everything is fine, huh?
Yes.
Okay, I'm so glad. How about you, Philip?
I'm good.
Awesome. Now, I have the alpha, and in order to find the sine of it, I know what's the trick. I have to project it there to make a right triangle on the unit circle. And you see that now I have a right triangle, but my right triangle is located on a unit circle. And now, I know that, guys, based on the things that we have learned, the definition of the sine of alpha represents what? Based on the things of right triangle, now this is on the unit circle. These two are just merged into to be one entity. The sine of alpha becomes what? Becomes, if you have alpha there, it becomes the length in the opposite of the alpha. That's right. We say that the opposite length divided by what? Divided by hypothesis, correct? Correct? And now, compare this formula with this. Compare these two formulas together. I say the opposite becomes, it's minus 8. What is the opposite of the alpha? It's this length, huh? I can call it then, it's gonna be 8. Divided by a hypothesis. Hypothesis is 17. No, that's not a unit circle anymore because the radius is not 1. Correct? And now, what is this length then? By using the Pythagorean theorem. Becomes 17 to the power 2. Can you do that on the calculator, guys? 17 to the power 2 minus 8 to the power 2 because 64. And take the square root.
It's
How much do you get?
15.
15, that's correct. Then I have 15. Guys, do you see the things which I'm writing? 17, 8, 15?
Yes.
Okay. And now, you see that now I have solved this triangle. Because I know all the length, 17, 8, 15. I have the alpha, that's normal, and that's 90 minus alpha. Then I know everything about that right triangle. Then I have everything, I know everything about the geometry and the trigonometry of this right angle. But what I was gonna do, I was trying to find the tangent of inverse of the sine of minus 8 divided by 17, which I called it alpha, the core of my function. Then the question is that now, the thing which I didn't forget it, I was looking for the tangent of alpha because I called whatever is inside as an inner function as the alpha. Then if I find the tangent of the alpha, it means that I'm totally done. Okay, now the definition of the tangent of the alpha. The definition of the tangent of what is that? Rose and Philip?
Yes. It's sine alpha.
Huh?
It's sine alpha divided by cosine alpha.
That's right. Sine alpha divided by cosine alpha. Let's do that way. I wanted to do the other way, but let's do that way. What is the sine of alpha, guys? There are two ways to do that, the tangent. We just do it by the rows. The sine of the alpha. How much is the sine of the alpha? The opposite length, 8, divided by the hypothesis, 17, correct? What is cosine of the alpha? The adjacent, which is 15, divided by the hypothesis, which is 17, correct? Rose and Philip, does it make sense?
Yes.
Yes, Philip? Okay, which essentially it becomes like what? You can just remove from 8 and 17. You can just have only the 8, the division of the ratio of what? 8 divided by 15, which is essentially the same thing that if you wanted to do by just having the opposite side, 8 divided by 15 as a definition of the tangent. And by doing that, essentially we are done. And yeah, we were able to solve this question.